Thank you very much, Mark. It is a pleasure to chair the two lectures of Professor Darrell Schlom. And maybe let me start by saying a few words on Darrell. Darrell Schlom is the Herbert Fisk Johnson Professor of Industrial Chemistry in the Department of Materials Science and Engineering at Cornell University. Darrell studied physics at Caltech. He then got a PhD at Stanford University, receiving an MS in electrical engineering and a PhD in material science and engineering. He was then a postdoc at the IBM Research Lab in Zurich, in Switzerland, in the Oxide Superconductors and Novel Materials group. Darrell is today a world leader in the epitaxial growth of oxide films and heterostructures using reactive molecular beam epitaxy. And his numerous contributions to the field of oxide electronics and materials by design, the idea to discover materials with properties superior to any known, have been really spectacular. So for his work and successes, Darrell has received numerous awards, including Humboldt Research Award, the Emeritus Medal, and the IOCG Frank Prize. He's a fellow of the American Physical Society, the Materials Research Society, the American Vacuum Society, and is a member of the National Academy of Engineering of the USA. He's also one of the most active members of the oxide electronics community. So it is really a great pleasure to have you with us, Darrell, for two lectures, one today and one on Wednesday. The lecture today will be 1 hour and 30 minutes, including eventually some questions. I remind you that you should use a chat to ask questions today. And we relay some of your questions, if time allows, at the end of the presentation. On Wednesday, I will give you the word for the questions after the lecture during the Q&A session. With this, Darrell, thank you again for being with us. The floor is yours.
Thank you, Jean-Marc. Good afternoon, everybody. It's my pleasure to talk about synthesis today. So I want to, today and Wednesday, we'll be talking a lot about synthesis and particularly the role of epitaxy in making oxide interfaces and heterostructures. So let's jump right into it. Of course, the reason to do synthesis is to unleash the incredible hidden properties that these quantum materials can have. And when you're thinking of unleashing hidden properties, you're probably thinking of alchemy, as Antoine Georges told us about last week. But what I want to show you is, in a sense, what we're doing is modern alchemy. In the way that we unleash these hidden properties is to use a bunch of thin film interface tricks. And I want to spend today talking about these tricks, and particularly, I'm going to spend a lot of time on strain engineering, an excellent way of altering the ground state of oxides, but as well as the other techniques that you see here. I'll introduce and go through them one at a time. Epitaxial nanocomposites, epitaxial stabilization, in which we stabilize the structures that are not the equilibrium ground state. Dimensional confinement. Here I'm showing, for example, the Ruddleson-Popper series, which again Antoine Georges spoke about last week. Interface engineering, which is very common in thin films, bringing materials together. Competing ground states that can happen across that interface. For example, the Lanthanum Titanate, Strontium Titanate interface that we heard about again last week. And finally, a trick in terms of breaking symmetry. A lot of properties come about from very low symmetries, and tricks that can be used to break those symmetries. So let's jump into the first one, which is strain engineering. So in the use of strain and appreciating how strain can affect the properties of materials has been, and particularly pressure, has been widely used in synthesis for more than 400 years. In fact, this comment was made by Percy Bridgman, the recipient of the 1946 Nobel Prize in Physics, when he talked about the strain, and he won the Nobel Prize for the invention of an apparatus to produce extremely high pressures and for the discoveries he made therewith in the field of high pressure physics. So this strain is hydrostatic pressure that's gone on for many, many years. And if I were to take an example of extreme pressures that can bring about new ways to put together materials, a great example would be this mineral, magnesium silicate, which happens to bear Bridgman's name. It's called Bridgmanite. And this mineral makes up most of the planet. So even though it's metastable and it takes very high pressures to stabilize it, so in this meteorite, to name a mineral, you have to be able to find it on the surface of the planet. So Bridgmanite was found in this meteorite recently, and the pressures and temperatures that this meteorite underwent to allow this phase to form were 240,000 atmospheres and 2,000 degrees C. So at those very high pressures, the perovskite structure, a very dense structure of combining magnesium, silicon, and oxygen, the structure that again, Professor George has introduced last week, this perovskite becomes the stable phase. And Bridgmanite is the most, by volume, it's the most common mineral of the planet. It doesn't, it exists mainly in the depth of the planet, and it makes up some 38% of the volume of the Earth. So indeed, perovskites are very common, and it's because of this high pressure that makes them possible. Now, those are examples of hydrostatic pressure. I'd also like to point out the important role engineering has played in semiconductors. So in the laptop that I'm using, the electronics that you're using, a lot of benefit comes from applying strain judiciously to improve the mobility of semiconductors, typically by 25 or 30%. And you can see that strain right here in these transistor structures. So we're seeing the gate, hopefully you can see my arrow pointing to the gate of the transistor and the source and the drain. And notice the contrast here, which is indicating how much strain, whether it's compressive strain with a negative sign or tensile strain with a positive sign in this structure. And that strain is what boosts the mobility of the channel of these transistors, and is an important part of the performance that we get in today's semiconductor devices. So strain engineering is old, and it's been applied in thin films for decades, and it's of course a very important production technique. The use of the realization that strain engineering was going to be important to semiconductors goes right back to some of the founding fathers of this area. You recognize Shockley and Bardeen on this paper from 70 years ago, where they were talking about how strain should affect the band structure of semiconductors. Now, an important difference between using strain to benefit semiconductors and what I'll be talking about in this lecture is that it's one thing to take the existing ground state and improve its properties. That's what's done in silicon transistors. It's still in the diamond cubic structure, but by applying the right kind of strain, it depends on the doping and the orientation, one can boost the mobility. In quantum materials, and in particularly in oxides, there can be competing ground states that are just slightly higher in energy. And a beauty of strain is that one can use strain to change the energetic landscape and stabilize what was a metastable material and make it the stable ground state under strain. So what I'm talking about is not improving an existing structure, but accessing a hidden ground state, which can have properties that are far better than what was the ground state, or in fact of any known material. And I'll give you a couple of examples of that in this lecture. Okay, so I said I was going to talk about synthesis, and I want to start with important synthesis rules, particularly for oxides. So Linus Pauling came up with 5 synthesis rules. The first of those synthesis rules has to do with radius ratios. So I went to the ultimate source here of Pauling's rules, Wikipedia, and you can see that in a picture what Pauling's first rule, which is considering anions and cations as spheres, is that you to make the energy as low as possible, you try to put as many anions around cations as you can fit. So you want to have the best Madelung energy contribution that comes from this ionic material. And so what's here is stable is when you've packed as many anions, those are the blue things, around a cation as possible. And what's listed here as unstable is when these spherical anions are overlapping. So now you're starting to get a lot of repulsion from these anions. You want to have the Coulombic attraction between the cation and the anion, but not that repulsion. So the stability limit, and Pauling worked this out for a bunch of different coordination polyhedra, so including in perovskites, the all-important octahedron, of what the radius ratio should be between the cation and the anion. And from Pauling's first rule, what we learned in synthesis is that the stability limit is when you just have the anions touching each other. Now, the opportunity arises in applying strain to go further and what I'll call break Pauling's rules. Now, here at Cornell, I should point out that our motto is break the rules. So it's with great pleasure that one can use strain, and in particular epitaxy, to break the rules. So I want to talk about it first from a cartoon standpoint. Epitaxy means that we start with a substrate that has a particular crystal structure, and we rain atoms down upon that substrate. And if the atoms that we're raining down would like to form the lowest energy interface that they can, if it's possible for them to follow the template that's provided by the substrate, that will provide for a very low energy interface. And there are limits to how far you can push this, but the idea is that by having a substrate that is, say, a little bit larger in lattice constant than the atoms that you're raining down on it would like to have, that instead of forming their equilibrium spacing, those atoms that you rain down on it will instead follow the larger spacing of the underlying substrate. Or it could be that you have a substrate, and this is again, PowerPoint substrate, that is a little bit smaller than the equilibrium spacing of the atoms that you're raining down on top of it. But to save the energy that it would cost at that interface by forming defects, as long as the film is thin and the strain is not too much, those atoms might like to follow the existing template of the underlying substrate and form with compression, biaxial compression, to follow the shorter distance of the substrate. So that's what's, I've tried to indicate here in this cartoon. Imagine the perovskite substrate that's pink and green here, having a spacing that's a little bit smaller than the atoms that we're raining down on top of it. And so those atoms form with biaxial compression. So it's biaxial because in my simple cartoon here, I'm thinking about putting a cubic perovskite on top of a cubic substrate. And so in order to make it fit, we squish it from both in plane directions. So it gets strained in plane. And in the out of plane direction, it's allowed to relax. So the stress-free in the out of plane direction. But this is a way of imparting biaxial strain. Now, if we think about what that's going to do to the atoms that are inside of these octahedral cages, let's consider this case here. Let's say that this case that I've shown here in the center, the one that's unstrained, is at Pauling's stability limit. So in that case, the green cation and if I think about the anions that are around it, this octahedron on each of its vertices has an oxygen, which I'm not showing because there are so many oxygens in this picture. I'm just showing the vertex, and at every vertex, there's going to be an oxygen. So the coordination polyhedron around this, and let's say there's ruthenium in the middle, for example, and then there's oxygens here. The coordination polyhedron is an octahedron, and if I was at a particular material where in bulk it just satisfied the stability limit, I could think of what happens when I use this strain engineering trick of providing these atoms that I'm going to rain down on the substrate with a substrate that's slightly larger in lattice constant. So that's what's shown here on the right. And if I think of following that existing template of the substrate, it means that this coordination polyhedron, this octahedron of the ruthenium, is going to get stretched in the plane. And when it gets stretched, I'm going to have the condition, which Pauling would call unstable, where I have this, I no longer satisfy the stability criteria for this radius ratio between the ruthenium and the surrounding oxygen. That this ruthenium, if you will, can rattle around inside of its cage. That's what I'm showing here on in the cartoon form. That the green ruthenium wants to get closer to either the oxygens over here on the left-hand side or closer to the oxygens over on the right-hand side, because it no longer can be up against all of them at the same time. The same kind of thing can happen, at least in cartoon form, over here on the left, where I again rain down atoms on top of a substrate that's a little bit too small, and now the coordination polyhedron gets squished in plane, so it gets strained biaxially, but it's stress-free in the out-of-plane direction, so it expands in the out-of-plane direction, and that gives this green cation room to rattle around in the out-of-plane direction, okay? So that's the way that it looks in PowerPoint, but it's clearly an opportunity to use epitaxy to break Pauling's rules. Now, how does this work in reality? Well, let's again look at the energy landscape first, and then let's look at the predictions of theorists from 2 decades ago of a perovskite system in which they predicted that indeed you should be able to change the ground state of a material. And the material that I'm talking about is strontium titanate. So the model system for all perovskites, a nice cubic perovskite at room temperature, but something that is centrosymmetric at all temperatures. So at all temperatures, the green titanium stays inside the middle of its octahedron. So if we look at the energetic landscape that the titanium sees in the equilibrium structure, it's sitting inside of essentially a parabolic well. But if we change the strain state by putting it in, say, in biaxial tension, now that energetic landscape that the titanium ion sits in is going to be lower if the titanium goes off center. So by going off center to the left, where to get close to those oxygens on the left side, it lowers its energy, or it can do by symmetry the same thing by going off center to the right. So in plane, you can see that there's now a much different energetic landscape. We've gone from having the lowest energy configuration with the titanium in the middle in a centrosymmetric crystal structure to one that has now broken inversion symmetry. And so this realization was made by this is a Swiss group, a Swiss and Russian group, and they predicted that the effect of biaxial strain, which is the horizontal axis that's imposed by a substrate, what that should be on strontium titanate. And it's a very colorful diagram, as you can tell, but the things to pay attention to are the superscripts. So the superscript P means that the material is para-electric. So it's, and that's where strontium titanate is normally. Strontium titanate normally doesn't have, it has a center of symmetry, so it cannot become ferroelectric. The superscript F, on the other hand, means ferroelectric. So you see there are a lot of different Fs, and those Fs correspond to, in this diagram, to different directions in which the polarization can lie. So for example, in tension, in biaxial tension, which is the right-hand side of the drawing here, which corresponds to this double well, it's favorable for the titanium to go off center, either to the left or to the right. When it does so, the titanium is a positive ion. So it's going to have a polarization when it goes off center to the left. That's going to be a polarization that's net to the left. Or equivalently, when it goes off to the right, it's going to be a polarization that's off to the right. So it's going to be an in-plane polarization. That's what's indicated here by this superscript F on the right side of the diagram with biaxial tension. If we look at what happens with biaxial compression, it again corresponds to the cartoon that I have, where the coordination polyhedron, the octahedron around the titanium, has elongated in the out of plane direction. So now the titanium can rattle up and down in this same double well. And it breaks symmetry, it goes off center, and that gives rise to a polarization now that is either up or down. So it's a different phase, and that's why it's indicated here by this phase, as opposed to that phase. Has different symmetry. This one's tetragonal, this one's orthorhombic. But you can see that the effect that was predicted on strontium titanate is huge in theory. And that's where experimentally we got involved in looking at what happens to strontium titanate from an experimental standpoint and putting it on top of substrates. And I'm talking about, for example, this dysprosium scandium oxide, dysprosium scandate. It's a perovskite. It's a perovskite that's about 1% larger than strontium titanate. So it corresponds to, cartoon-wise, to the sketch that's over here on the right. And from this theory, we would expect that to make strontium titanate ferroelectric. One way of looking for ferroelectricity is to look at the dielectric constant as a function of temperature and look for a peak. Strontium titanate itself, as a bulk material, has a dielectric constant versus temperature, which is shown by this blue dashed line. This is the measurement of Alex Mueller from many years ago. And what he saw was that the dielectric constant increased with decreasing temperature and never went through a peak. It reached a peak. It's on the verge of going in through a ferroelectric transition. That's why I say that it's almost at the limit of Pauling's rules. But it goes into what Alex called a quantum paraelectric state with this very high dielectric constant. On the other hand, when we strain strontium titanate commensurately, so this film is 50 nanometers thick, you can see that there's now a nice, clearly defined peak in the dielectric constant. So it obeys Curie-Weiss law. And if we strain it even more by putting the strontium titanate on top of gadolinium scandate, you can see that this peak, which is telling you where the material becomes ferroelectric, where it goes from being paraelectric to ferroelectric, that transition temperature goes above room temperature. And it's possible now, even at room temperature, to see this ferroelectric ground state stabilized using this strain engineering trick. Okay, so there's an example in a simple way of taking a material from a ground state that is not ferroelectric into a ground state that is ferroelectric. So using strain engineering to alter the landscape of energetics. Now I want to show you a more interesting quantum material. That's the magnetic version of strontium titanate. So this is europium titanate. Europium is in the rare earths, and it has a very, so it's going to be europium 2 plus, titanium 4 plus, oxygen 2 minus, ionic material, an insulator. And I mentioned it's just like strontium titanate in the sense that it's a perovskite. So in bulk form, it's cubic at room temperature, has a lattice constant of 3.905 angstroms. It's just like strontium titanate. Strontium titanate is also cubic in the perovskite structure with 3.905 angstroms. Okay, so this is a great example of bringing in magnetism to the strontium titanate, which normally was so that this was everything was full shell, so there was no unpaired electrons. But here for europium 2 plus, that's going to be a half-filled F shell. So there's going to be 7 unpaired electrons. So 7 more magnetons are localized on these europiums. That's a big opportunity to see what happens with epitaxial strain. So I'm going to show an example that is putting europium titanate under biaxial compression on top of the substrate LSAT, about 1% biaxial compression, and also in about 1% biaxial tension on top of dysprosium scandate. So first of all, what does theory say should happen? And like the theory that I showed you a minute in the last slide, this theoretical prediction was also a prediction. Okay, so I want to emphasize that there are bold theorists who make predictions and publish them and say, if you put the atoms here, that you should get these properties. This is another example of a bold prediction, and this prediction is by Craig Feeney, my colleague here at Cornell, and also in his thesis advisor Karen Rabe. This was the last prediction that Craig made as part of his thesis. But his prediction looks like the strain phase diagram that you see here, that at 0 strain, which would correspond to putting europium titanate on top of strontium titanate substrates, he predicts that the ground state should be the same as bulk europium titanate. It should be simultaneously paraelectric and antiferromagnetic. So if we look over here to the cartoon, the europiums indeed all have 7 Bohr magnetons on them, but they're arranged in it's a G-type antiferromagnet. So the nearest neighbor europiums are all antiferromagnetically aligned with respect to each other. So overall, there is no net magnetization in europium titanate. Some of my colleagues would call europium titanate in its bulk form doubly boring. It's antiferromagnetic and paraelectric at the same time. But what Craig and Karen predicted was that landscape should change with either biaxial compression or biaxial tension. And the ground state should change to be simultaneously ferromagnetic and ferroelectric at the same time. In fact, their prediction was quite astonishing, because they predicted that this material should have robust ferromagnetism, 7 Bohr magnetons, at the same time that it has robust ferroelectricity, about 10 microcoulombs per square centimeter. So, which, if true, would make it the world's strongest multiferroic material. So, of course, there was a lot of experimental work, and we were actually the 4th group to publish on this, but I'll tell you about our results. But I also want to talk first about the inner workings of Craig's calculations of what's going on. So europium titanate, I mentioned how the europium is the only atom in europium titanate that has unpaired spins. It's got it's got a half-filled F shell, so 7 Bohr magnetons on the europium. And the europiums have exchange interactions with nearest neighbor europiums, or second nearest neighbor europiums, or third nearest neighbor europiums, et cetera. And on the computer, Craig can calculate what the strength of those magnetic exchange constants are, those J's that describe the coupling, whether those couplings want to be ferromagnetic, whether the spins want to align, which would be a positive in a positive J, or whether they want to be antiferromagnetically aligned, which would be negative. Now, so a beauty of being able to do first principles calculations is that Craig could calculate what each one of these terms was. And if he looks at both the case of unstrained bulk europium titanate versus, for example, putting it on LSAT, which is going to be biaxial compression, he can see how those exchange constants change with strain. And when he looks at bulk europium titanate, what he sees that is the nearest neighbor exchange interaction, so this is between europium and europium direct exchange, is positive. So it would like to be ferromagnetically aligned. If he looks at the second nearest neighbor interaction, which I should point out is super exchange through an intervening oxygen, there are second nearest neighbors, both in the plane as well as diagonal here. One of them is ferromagnetic, and the other one is antiferromagnetic. And also there's the third nearest neighbor interaction. And the third nearest neighbor interaction is also super exchange through the intervening titanium, which I mentioned is in the center of this. It's a cubic perovskite. So the titanium is in the center of this cage. And so that gives rise to this third nearest neighbor exchange interaction. And that third nearest neighbor interaction, and you can see that there are 8 of them along the body diagonals, are all antiferromagnetic. So overall, in the computer, when Craig calculates this, the overall magnetic state, and one has to take into account the first, second, and third nearest neighbor interactions, the third nearest neighbor interactions that are antiferromagnetic dominate, and overall, europium titanate in bulk is antiferromagnetic. But you've noticed that the first and second nearest neighbor interactions are mainly ferromagnetic, and it's the third nearest neighbor that tilts the balance and makes europium titanate overall antiferromagnetic. Now let's imagine what happens when you put europium titanate in biaxial compression. So biaxial compression corresponds to this cartoon that I have over here on the left. And in the computer, what that looks like is that the titanium, or even at least in PowerPoint, okay, you can see that the cage is elongated in the outer plane direction. So the titanium wants to go off center so that it can bond to these oxygens that are on this side of the octahedron. When the titanium goes off center, that affects the super exchange along the body diagonal. So what was effective antiferromagnetic super exchange through the titanium is going to be weakened as the titanium goes off center. So this is a great example of how ferroelectricity can be enhanced at the same time as ferromagnetism in this quantum material europium tightening. So you can see how biaxial strain, not only is it like strontium titanate, and it's going to break the center of inversion here by taking the titanium off center, but also it's going to change the balance between the exchange constants being ferromagnetic or antiferromagnetic. And so that's why when you, at least on the computer, when you strain it enough in biaxial compression, it should go off center enough that it becomes ferromagnetic and ferroelectric at the same time. Okay, so I've given a long-winded explanation of the inner workings of the material. How does this look like in experiment? What we saw in experiment, and we did many control experiments too, but we saw that when we looked at the unstrained europium titanate on strontium titanate, as well as biaxial compression on LSAT, and this is a magneto-optic Kerr effect, neither of those show any evidence of ferromagnetism, whereas when we strain it in, these are all commensurate films, so we kept them thin. When we strained it in biaxial tension, then you can see from the magneto-optic Kerr effect, there's a robust ferromagnetic state. We also looked at the ferroelectricity. Here we use second harmonic generation. And you can see from the second harmonic generation reconstructing the hysteresis loop, showing that it's simultaneously ferroelectric and ferromagnetic by putting it on top of a dysprosium candidate. So here I hope that I've emphasized the inner workings of what's going on inside of this material for this relatively simple example of how you can change the ground state of a quantum material. Now, having said that, you might go, wow, this is easy. Think of all the things that you can do with strain engineering to change the ground states of oxides. And indeed, many cool ground states have been accessed using strain engineering. But I want to tell you about how there's more to the story, and there are limits on what can be done. So let's talk about the first limit. It's great to be able to strain things by huge amounts, and you can be thinking about how that's going to affect the band structure and give rise to all sorts of new phenomenon. But nature, of course, is always going after the lowest energy state. So when you strain a material, you increase its energy. And the green curve that I show here is showing, as a function of film thickness, how straining, it increases the energy. as you make it thicker, you have more and more volume, and that strained volume costs you more and more energy. So the energy goes up linearly as you increase the thickness of the film. There's another alternative that nature could take, and that is to relax the strain in your film. And one way to relax strain is through the introduction of dislocations. So in this cartoon down here, imagine that I have a substrate with a smaller lattice constant than, I have a substrate with a larger lattice constant than that of the film. So one way to relax the film is to introduce a bunch of dislocations. So here I schematically have a bunch of an array of edge dislocations. And so I make that array, and this array will release that biaxial strain, but it costs energy because there's a strain field associated with each one of these dislocations. So that's going to cost me energy, and it's going to cost me energy at that interface. So if I look at, that's the red line here, how much it costs to introduce dislocations, and I look at this as a function of thickness, I have this 1/over thickness energy fall off of what I get from putting dislocations in the film. And you can see that energetically there's a stable point, okay, where the material would go from a lowest energy state of being strained to a lowest energy state of being dislocated. And that calculation was done almost 50 years ago by John Matthews and Blakesley in this classic publication. For those of you that are students, you probably have never heard of John Matthews, but maybe you've heard of his son, Dave Matthews, from the Dave Matthews Band. It is indeed the same Matthews. And what he calculated was the equilibrium critical thickness at which energetically the system would have a lower energy by being in this dislocated state rather than the strained state. Now, so here you see the energetics. I want to point out that we call this a critical thickness. It's common to be able to go beyond this critical thickness because there's an activation barrier to bringing in the dislocations. So yes, if you're at high temperature and dislocations can nucleate and move around well, then you'll get closer and closer to this equilibrium critical thickness. But if you're at low temperature and you're in a system where it's hard to bring in dislocations, then you can typically go beyond this equilibrium critical thickness. And if I show what really happens in films, so here as a function of thickness, when one gets beyond the critical thickness, now it's energetically favorable to have dislocations there, but one needs to nucleate them. One low energy nucleation path is the introduction of half loops from the surface of the growing film. And then those half loops, if they can move down to the interface and become misfit segments, like I've shown here on the schematic on the right, that can proceed. That takes film growth. So you shouldn't be thinking about the strain going away suddenly, from fully strained to fully relaxed. What happens in real films is that when one goes beyond the critical thickness, and often substantially beyond the critical thickness, just to give you a rule of thumb, for many of the perovskites that we make, we can go about a factor of 4 thicker than the equilibrium critical thickness that you calculate from this Matthews-Blakesley formula. Before we start to see the onset, where we can just start to resolve. So using a synchrotron, to start, because the films are thin, to start to be able to see relaxation. Typically it's a factor of 4 thicker. And then as the film gets thicker and thicker, you start to see that strain relax. It relaxes in a very inhomogeneous way. There are these inhomogeneous strain fields. Okay, so for doing strain engineering, I really recommend staying in the regime where one has a commensurately strained film, where there are not a bunch of dislocations that have inhomogeneous strains, but rather one can see the intrinsic properties of the ground state that you stabilized in this homogeneously strained commensurate film. Okay, so one of the realities is a finite thickness. So it's great to have huge strains. The bigger you make the strain, the thinner will be the critical thickness. So the strain is this F parameter down here. Okay, so they're inverse to each other. And I'll talk about what state of the art today is in terms of strain, but there's going to be a definite trade-off with how thick you can make that film as you go thicker. Typically 3% is about the maximum that can be done in perovskites. But there's another way that films can relax. They can crack. And again, this was calculated about 50 years ago by the same John Matthews. And this nice, here's the formulas, and this is now the equilibrium critical thickness for the formation of cracks. It's actually the thickness at which it's stable for existing cracks to propagate in the material. I'll say more about that in a minute. But what Matthews calculated in this nice diagram is, as a function of film thickness, how it is that he would, from an equilibrium perspective, expect the material to behave. In this lower left quadrant of misfit, and this is so 1% is here, 8% is about here. Okay, huge strains. The homogeneously strained portion where we want to be if we want to use the strain engineering is down here in this lower left. When one passes this first line, this is where one passes the equilibrium critical thickness for dislocations to come in, like I talked about in the last slide. So in this above line C here, it's now favorable for dislocations to form to relieve all of that strain, but it takes there's a nucleation barrier for that to happen. It could be that you have a really strong nucleation barrier. Maybe you're growing at a really low temperature, or maybe you have a system where it's very hard for dislocations to nucleate and to move. So there becomes another regime that becomes important, and that's where films can crack. And for those of you that do synthesis, maybe you've seen cracks in your films. That means that you're doing a great job at keeping the dislocations at bay. But if there are pre-existing cracks in your films, once you get above line A here, it's then favorable for those cracks to propagate. Matthews also calculated at what strain, that's this line B here, cracks should spontaneously form. Okay, and there you can see, very well, from my perspective, very large strains, but it's important to keep these relaxation mechanisms in mind when you're thinking of how you're going to access this ground state. This is the reality that keeps in. Now another important reality is another way, other than relaxing through dislocations or cracking, but another way in which the system can accommodate the different size substrate that you presented it with. And one way that it could accommodate that is it could form some defects, and those defects cost energy, but maybe those defects are ones that make it so that the material matches better to the substrate, and you get a payoff in all that elastic strain energy that you can put into the defect energy. Now, to explain this, I want to use what's called a Heckman diagram, which is a diagram that relates stimuli to properties. So, for example, if on this vertex over here on the left, I see somebody has mastered the annotate feature, which is good. Anyway, on this Heckman diagram over here on the left, the outer vertices are the different stimuli that you can tweak a material with. So, for example, you could apply an electric field to a material. And when you apply an electric field to a material, the response of the material is you can polarize it. So you can have a polarization that forms, and the property is that relates these two things to each other is the susceptibility. If we want to relate E to D, the electric displacement, then it would be the permittivity along this vertex. Okay, here's another such stimulus response relationship. So you apply a magnetic field and you change the magnetization, the magnetic permeability, stress and strain related by elasticity. Okay, so these are common properties that we've seen. But what I want to to bring in here is the concept of what can happen when you change the chemical potential of the system, or the conjugate thermodynamic parameter, which would be the composition of the system. So just like, here stress and strain are conjugate parameters that make up these kind of diagrams, here are the conjugate parameters that become relevant for bringing in these kind of compositional defects are the chemical potential and the composition. And this effect has a name. It's known as chemical expansion. I'll tell you more about it in a minute. But I thought I would just, if you're still pondering this diagram, say a few more words about it. These kind of diagrams are called Heckman diagrams because it was Heckman who almost 100 years ago now, so 95 years ago, Heckman, in his classic paper, talked about the properties that relate stimuli and response functions. So here you can see it's obviously a German publication, but talking about the effect of changing the temperature and the heat capacity of a material, talking about the elasticity, dielectric constant. Okay, so all these nice properties. This was later generalized in this book by Nye to show the diagram that I just showed you a few minutes ago. And if we update this to more recently, you can imagine. I mean, it's nothing special about triangles or tetrahedrons, but this is just a way of thinking about all of the different thermodynamic parameters that you can use to tweak a material and how it responds and the properties that relate the responses. So today in multiferroics, we're very interested in applying electric fields to change the magnetization, okay, or the magneto-electric effect, which would be the converse effect, which is thermodynamically equivalent. But I think in Professor Bibas's talk, you saw such a diagram, but I want to come back to that same kind of diagram and talk about this important extra vertex. Okay, so it's actually, I'd like to have 5 vertices, to really show them. Well, just to show many of the thermodynamic parameters. You see temperature is missing here, but here, by adding this vertex of chemical potential, we can think of what the effect of the chemical potential could be on the deformation of the material, on the shape of the material here. So the effect of chemical potential on strain. So there is such an effect, and I'll show you as a direct effect. So you change the chemical potential. Maybe you change the pressure at which change the oxygen partial pressure. So that would change the oxygen chemical potential. And by doing that, the material might react by forming oxygen vacancies, and having a lot of vacancies in the material might affect the shape of that material. So I can talk about a strain that comes from changing the chemical potential. Similarly, there's the conjugate parameters here. So there's going to be the converse effect, where I can think of the stimulus now being stress and how that can affect the composition. So this comes into play with these large kinds of strain engineering that we're talking about. Okay, so first of all, just an example of a material where changing the chemical potential can change the size of the material. Okay, so here you may recognize this magnetically ordered material. And so lanthanum, strontium, cobalt oxide. It's a nice perovskite material. From a chemical standpoint, the cobalt in this material is a mixture of 3+ and 4+. 4+ cobalt, it takes very high oxygen pressures to stabilize. So it's common for this material, if you want to make it oxygen 3, not 3 minus delta, to use pressures like 5,000 atmospheres to drive oxygen toward 3 and see the true intrinsic behavior of like strontium cobalt oxide, which my multiferroic friends got interested in, but I was, from an experimental standpoint, that's a lot of pressure to try to make in a vacuum system. Anyway, strontium cobalt oxide is hard to make because it's hard to make cobalt in the 4+ state. And similarly, if you take even lanthanum strontium cobalt oxide and you put it in vacuum. So if you go from being in air to being in vacuum, and you're patient, so notice that the time scale here, this is a bulk sample, but the time scale here is in hours. What you can see is even though you're not doing anything, okay? I mean, you're not, the thing is changing in size, okay? So you see as you change the chemical potential, the material changes its size, okay? So I can define a strain, some delta L of this rod that accompanies this change in the chemical potential. Well, if changing the chemical potential strains the material, then I have to think about the converse effect, which thermodynamically, this same property must be the same. This second rank tensor that describes this property, relating stress to changing the oxygen composition of the material. And this is through oxygen vacancies. In fact, in lanthanum, strontium, cobalt oxide, this is well seen, it's well documented in thin films of lanthanum, strontium, cobalt oxide, that if you try to play this strain game, as I'll call it, taking a substrate, in this case, lanthanum aluminate, which has a smaller lattice constant than lanthanum, strontium, cobalt oxide, versus strontium titanate, which has a larger lattice constant, you can see a total difference in the defects that come about in this material. Now, the defects are indicated by these lines. These lines, according to these authors, are oxygen vacancies that have come in as planar defects. And you can see that in the case of strontium titanate, where the material is in biaxial tension, that those oxygen vacancies have aligned, again, in a biaxial way, as planes to accommodate, through defects, the change in the lattice constant between the substrate and the film. On the left-hand side, by putting this on a smaller substrate, again, those planes of oxygen vacancies exist, but their orientation has switched to make it so that overall it has a lower energy to go on this substrate. So this is going to make it so that it's smaller in plane. This makes it bigger in plane. So this makes it better match to the substrate and reduce the elastic energy. Now I've deliberately shown an example of cobalt 4+, which is a system where these vacancies are well known. See if I can go back a slide. So here's a system where this effect has coefficients that are large. Okay, you change the chemical potential, you have huge change in strains. Now, seeing this, I should point out that it's system dependent how large this coefficient, this second rank tensor T is. In some systems, like the cobaltates, or systems where you're trying to stabilize some hard to stabilize oxidation state, the effective oxygen partial pressure can have a huge effect on the system. In other systems where, let's say, lanthanum aluminate, it's a great example. So lanthanum aluminate, lanthanum is 3+, aluminum is 3+. Those are the only oxidation states that are known for those elements. So this tensor coefficient, although it is some finite value, is very, very small and can be neglected. In the case of lanthanum cobalt oxide, this coefficient is huge and it cannot be neglected, and it will swamp the effect that you may be trying to see through strain. Okay, so I'm telling you, the additional complications to the story. The last one I want to talk about, since we're talking about perovskites, is the concept of octahedral rotations. Now, I've spent a long time talking about the biaxial compression, and I had a simple cartoon picture that looked like this, and biaxial tension, and I had a simple cartoon picture that looked like that, where all we thought about was uniformly distorting that octahedron. But as, again, Professor George talked about last week, the reality of the situation, particularly with perovskites grown in the 1,0,0 direction, is that these octahedra can do more than simply uniformly compress together biaxially or extend together biaxially. They can rotate. In fact, many perovskites are famous for having these rotations. When the tolerance factor is equal to 1, that's when you should have a nice cubic perovskite with no octahedral rotations. But as the tolerance factor gets less than 1, that's where it becomes favorable to have the this octahedra rotate in the language that Antoine talked about. So you have a rotation around the c-axis. No, I misspoke. Okay, it would be yeah. Okay, sorry. So in the case of compressive strain, another way to take that up is you can just simply rotate the octahedron, and that brings everything smaller in plane. Or we could do what's called tilting, which is a rotation along an axis that's in the plane. So these alpha and beta angles here are in the plane of the substrate. And if we tilt by one of those axes, then it gets longer in the plane, which would be a way to accommodate the different lattice constant of the substrate. Now, perovskites themselves, deviate from having a tolerance factor of 1, and as they have tolerance factors that deviate from 1, in fact, most perovskites do not have the cubic perovskite structure, and the way that they accommodate that tolerance factor is to bring in rotations and tilts. So it's well known in perovskites. In fact, most of the substrates that I showed you have rotations and tilts in them. And so you might, now that you're thinking more richly about what can happen to raining down a perovskite on top of a perovskite substrate, you might be thinking about, well, how does it inherit that rotation pattern coming from the substrate, and how might it accommodate the strain by doing rotations and tilts rather than the simplistic picture that I showed you above. So let's again look to experiment to see what's going on. And here's a nice case of calcium titanate rained down on 2 substrates that are almost the same in their lattice constants. So neodymium gallium oxide, everything on this diagram is a perovskite. So these are commercially available perovskite substrates on the bottom. Okay, and calcium titanate has a lattice constant, well, a pseudo-cubic lattice constant that's shown here. Okay, I should point out that all of the lattice constants that I'm showing here are pseudo-cubic to keep things simple. In reality, the cubic materials on this diagram are things like strontium titanate, europium titanate. Okay, those are great cubic tolerance factor equal 1 examples. Potassium tantalate is another example of a cubic material. LSAT is also well, okay. It's very close to being cubic. If you look at great detail at the lattice constant, it has a slight tetragonal distortion. Okay. Neodymium gallate, on the other hand, is definitely orthorhombic, and it's got a lot of rotations going on. So, but from a pseudo-cubic perspective, if we just look at if we treat them as look at the volume of the unit cell and what that pseudo-cubic lattice parameter would be by saying it's a cube, okay, they have almost identical pseudo-cubic lattice constants. They differ, so one's 3.86, one's 3.87 angstroms. Okay, so they differ by 100th of an angstrom. And this example of calcium titanate is a nice example because it points out, what happens when you rain the same material down on top of 2 substrates that you would think are going to give rise to very similar strains. So in the one case on neodymium gallate, you'd expect a biaxial tension of 1.1%, and in the case of LSAT, 1.2%. Okay. Now the reality of the situation is shown by these cross-sectional TEM images, where the authors have mapped out the octahedral rotations, and that's shown in the cartoon on top of the annular bright field data. So the substrate, and here you see a high angle annular dark field, so you can see Z contrast, see the lanthanums in the LSAT substrate. And here the calcium titanate, the calcium is much lower Z, so you also see it, but you can see there's a nice sharp interface. And then looking at the annual bright field to get a better idea of what's going on, in particular with the oxygens, to see those rotations. you can see that the story in going from LSAT to calcium titanate looks like one in which the LSAT has no rotations. So I mentioned that LSAT is very, very close to being cubic. It's slightly tetragonal, but okay. Even in tetragonal, the Glaser notation to describe the rotations along the axes, this A, B in-plane axes, and the C out-of-plane axis, would be that there's no rotations. Okay, so we go from having a substrate with no rotations to calcium titanate, which has rotations. So in bulk, calcium titanate, the orthorhombic PNMA rotation sequence is an out-of-plane rotation along the A-axis, an out-of-plane rotation along the B-axis, and an in-plane rotation along the C-axis. This notation I know you learned about from Professor George's last week. So let's see what happens in reality. And that is shown here. You can, hopefully you can see by eye that at first there's very little, it follows the rotational pattern of the substrate, but then over time, it reaches a steady state value, which is what's called the bulk value. I don't want to, it doesn't mean the bulk of calcium titanate, because this is strained. It's strained by about 1.1%. But it means that it's no longer changing, okay? So you can see that there's a few unit cells, a couple of nanometers, in which the octahedral rotation pattern evolves from that of the substrate with no rotations to that of the steady state film, which has rotation angles, and it's particularly, we're talking about this angle beta, which is one of the in-plane tilts. Okay, if I go back here, talking about this beta angle, it's an in-plane tilt that's gonna accommodate the fact that the substrate we're putting on this on, so LSAT is larger in size than the film. And that gives rise to these angles that you can see are quite large. So about 10 degrees are happening. If we contrast that to what happens in going from neodymium gallate to calcium titanate, neodymium gallate has the same space group 62 PNMA as calcium titanate. So the octahedral rotation pattern of neodymium gallate is the same as the octahedral rotation pattern of calcium titanate. So although the pseudo-cubic lattice constant of neodymium gallate is almost identical to that of LSAT, notice this huge difference in how these octahedral rotations evolve, okay? The final state is actually quite similar. You'll see there are 10-degree rotations in both of them, but the substrate neodymium gallate started with huge rotations, and so those rotations, evolved to, whereas here, they started with 0 and worked its way up to that of calcium titanate. So here I'm showing you that this is a richer scenario than simply, immediately having this strain. Even in a fully commensurate film, there is this regime in which you can have these octahedral rotations evolving from the interface into the film. And the length scale over which those octahedral rotations evolve can vary depending upon what materials we're talking about, as well as even what intermediate materials there are. So here's a beautiful example from Rinder's group in Twente, and where they've put lanthanum strontium manganite, a nice quantum material, on top of neodymium gallate. So this is biaxial compression, if we just think of things as pseudo-cubic, of about 0.4%. But in mapping out the octahedral rotations, which you can see in this nice colors indicate clearly where the interface is between the lanthanum strontium manganite and the neodymium gallate. The lanthanum strontium, the neodymium gallate has these clear octahedral rotations, and you can see that those rotations are inherited by the film, but it makes its way toward a steady state, and that decay length of those rotations is a few unit cells. It's several nanometers. they also looked at what happens when you put an intermediate layer, so starting from a neodymium gallate substrate, putting an intermediate layer of strontium titanate, which has in bulk no octahedral rotations. What they see is that strontium titanate, the octahedral rotations fall off from the neodymium gallate, eventually reach no octahedral rotations, even though this is a fully commensurate film of strained strontium titanate. Okay, and then when they grow the lanthanum strontium manganate on top of it, there are no octahedral rotations that follow. The most dramatic case is over here on the right. A single unit cell of strontium titanate drastically damps the octahedral rotation decay length in this material. Okay, so now with this added richness of octahedral rotations, you can think of going from the substrate to going from deep into the film where there's a steady state, well, not so deep that you've started to have dislocations or cracking, okay, but deep enough that you get to the steady state strained value of the octahedral rotations in the film. And there's this transition region where you go from the octahedral rotation pattern of the substrate to that of the film. And this, of course, brings apart, not only the richness of the system, but also the opportunity that, what I'm calling strain engineering in the case of these perovskites also is the opportunity to do octahedral rotation engineering. And it may be that you want to have, that maybe you're going to get the properties that you want from this interface region, from what I'm calling the near field region, the region that's close to the interface, where you're damping this. It has the opportunity to change the properties, and indeed these authors found changes in the magnetic properties. A huge boost came about by changing the octahedral rotation pattern in the Curie temperature of the lanthanum strontium manganate. Other groups have found that in strontium ruthenate, the same. In fact, it was in close issue. It was very close in time. Both groups independently found that they could have these intermediate layers between magnetic layers. So in this case, it's lanthanum strontium manganate, and in the case of the group from Kyoto University, it was the strontium ruthenate. But again, changing the magnetic properties that came about from this intermediate layer. So there are more opportunities, I would say, than the simple cartoon that I showed you at the beginning would lead you to believe that can come from strain engineering. Okay, so the last thing I want to say about the octahedral rotation issue is everything I've been talking about up to now has been with 100 as the growth direction of the perovskite. And with 100, go back a second, the connection between the substrate and the octahedra is just at a single vertex. So it's at a point. And you can imagine, having rotations and rotations that damp and fall off as you go further away from that point. Now, what our moderator has discovered is that by changing the connection at the interface, instead of being through a single point of the octahedron, by making it a 1-1-1 oriented octahedron, now there are 3 oxygens that connect together, which drastically frustrates the rotation of that octahedra. So there's all sorts of opportunities to do octahedral rotations as well as to thwart them. I should point out that in this case, as you go from 100 to 111, other complications can emerge. So in most perovskites, the low energy surface, so for a nice smooth film, is the 100 surface. 111 surfaces can have higher energies, but Professor Truscon and his group were able to find growth conditions that yield very nice smooth surfaces. You can see that from the AFM in the background. You can also see that if you read the X-ray diffraction, there's these beautiful thickness fringes. So it is possible to make very nice superlattices that have smooth surfaces while thwarting octahedral rotations and using this to take advantages of the properties that you can get by tweaking these quantum materials through strain engineering. Okay, now I've spent a long time on this strain engineering, telling you not only what its capabilities are, and hopefully got your interest in using it. It's a very powerful knob, but also some of its limitations and things to be thinking about. And I think that this quote from Richard Feynman sums it up well. The need for control experiments. And when in his graduation speech, he talked about what he would call the first principle of being a responsible scientist is that you must not fool yourself. So you've got some idea of how you're going to use octahedral rotation engineering, strain engineering to access some hidden ground state. And maybe in your initial experiments, you see the kind of data that you're hoping to see. But you have to remember that you are the easiest person to fool because you already have this preconceived notion of what should happen. So the importance of control experiments is as an experimentalist, a very important knob. And I thought I'd just take this as an opportunity to come back to this example I showed early on of europium titanate. So europium titanate is a great example of changing the ground state through strain engineering. And I mentioned that we were the fourth group, I think, to publish on europium titanate. And I should point out that the first three groups saw that no matter what they put the europium titanate on, it was ferromagnetic. Okay, so let me show you that. So so this is to me a great control experiment. Here's the properties, the magnetic properties of bulk europium titanate are shown by this these upside down triangles, the one that says ×10. So this is looking at bulk, and in bulk europium titanate is anti-ferromagnetic. Okay, these thin films grown by these different groups on strontium titanate. So this is the non-magnetic version of europium titanate. It has a lattice constant of 3.905. Europium titanate has the same lattice constant with an experimental error. So these things are beautifully lattice matched. They have no octahedral rotations. They're both cubic materials. So how is it that when you make this thin film on a lattice matched substrate with no rotations, that you should see ferromagnetism? Okay, and what this group saw in their film is clear ferromagnetism. This other group here, in fact, they tried it not only on strontium titanate, they tried it on lanthanum aluminate and LSAT. So things with totally different strains. No matter what they put it on, it's ferromagnetic. And you can see clear hysteresis loops. Now this in one sense, it points to the fragility of navigating the landscape in quantum materials. To me, the excitement of oxide quantum materials is that you have nearby ground states in energy. And it's nice to be able to go from one to another. Of course, if you have things that are nearby, you have to be thinking about other ways that you can get there. I mean, these are very sensitive materials, okay? And so here you're seeing the sensitivity to the growth technique itself. So these films were made by a technique, pulse laser deposition, and the groups that made them found it was ferromagnetic no matter what they put it on. And that can be very useful, okay? So I'm not saying it's not useful, I'm just saying it's not the intrinsic property of the material. So here's, again, evidence that something strange is going on. I showed you first the magnetic properties. I want to show you now the structural properties. So this is europium titanate film. You're raining europium, titanium, and oxygen atoms down on top of a strontium titanate substrate. And in all three of these groups, in making their films by pulse laser deposition, what they see is that the film has a different lattice constant than the substrate. Now that's to be expected if this is a mismatched system, but these things are both 3.905 in bulk and with no octahedral rotation. So you go, what's going on here? But you can clearly see it. Here you see the thickness fringes from the film. This is my colleague Joel Brock here and Yuri Suzuki at the time at Cornell. The film peak is here. The substrate peak's there. If you look at this other group, here's the substrate peak, the nice intense one. Here's the film peak. Here, again, a bunch of different substrates, and the F is showing you where the film is. So even on the substrate that's lattice matched, the film is in a different position. On things that are mismatched, it can be even further away. But you see that something is going, so I'm just pointing out the importance of a control experiment. So in we did exactly the same control experiment using a different technique, molecular beam epitaxy. And I'll point out that a difference in MBE is that it's a very gentle technique. So there are no high energy species. Everything is thermal evaporation. It's just KT, hundredths of an electron volt of the energy of the species coming in. So in doing the control experiment, what we saw was, first structurally, that the substrate peak and the film peak, which you see the thickness fringes here, are on top of each other. So this is when you zoom in. Okay, you don't see them on top of each other zoomed out, and you see they're on top of each other zoomed in. Also, when we look at the properties, we see that it's antiferromagnetic. So it may seem very boring to not just jump to the exciting system and say, I've got this great idea, let's strain engineer it. It's always good to check and make sure that, just remember that you're the easiest person to fool. Okay. Now, I want to leave you with some guidelines on how much strain can be imparted. This is a very powerful tool. And I've talked about the different things that can go wrong, okay? the different way that nature can respond and find energetically less expensive things than straining your film. And how that trades off with, of course, the thickness of the film. What's common in perovskites is that it just is a rule of thumb. 3% is about the max that you can get in a lot of different perovskite systems. Now, if I were to tell you, what's the biggest in the literature that I'm aware of in a film using this strain, using epitaxial strain from the substrate approach, is 6.5% compressive. And it's bismuth ferrite, but in my view, it's a cheat because, and you can see that from the first principles calculation here. This is looking at the energetics of, so this is the 6.5% is bismuth ferrite on top of yttrium aluminate. Indeed, the bulk phase differs by 6.5% from this orthorhombic perovskite. But what you can see in the first principles calculations is there's another ground state over here. So there's like a parabola in strain around the bismuth ferrite rhombohedral phase, and then there's another parabola in strain around this this tetragonal-like phase, this super extended ferroelectric phase over here, and that lowers the barrier. I mean, bismuth ferrite it's amazingly malleable, but it really helps when you don't have to pay the full energy cost to do the 6.5% strain. So I'm just saying that there are some systems that you can get lucky and go to even higher strains. Another powerful way of imparting strains is to make the films super thin as a membrane and then lift them off and strain them without the substrate in place. And I don't want to, I know that I think it's the last lecture in the summer school is given by Harold Huang, so I won't steal his thunder, but I just want to give you an idea of the amount of strain that he's demonstrated. It's a whopping 8.2% uniaxial tension or 5% biaxially. So huge strains are possible. These are, again, very thin membranes. Now that's all in perovskites. But of course, the world of quantum materials and oxide quantum materials is much broader than perovskites. So I thought I'd end by showing you some unpublished data. It's hard to give an hour-and-a-half lecture with talking about published stuff. So I thought I'd have some fun here at the end and tell you an example, well, two examples of non-perovskite strain engineered materials. The first one is a rutile. It again involves octahedra. I'll show you the crystal structure in just a second. But in terms of strain engineering, the amount of strain in the system is a compressive strain of almost 5% in one direction. It's a huge strain. And you might go, well, how is that possible? Let me point out the quite low substrate temperature. So if you're used to making perovskites in oxides, typical substrate temperatures might be 700 degrees C. These rutiles have an advantage in that they can be grown at much lower temperatures. So let's have a look at the data. Oh, and what has that allowed us to do? It's allowed us to turn on superconductivity in this otherwise non-superconducting system. To my knowledge, it's the first example of strain stabilized superconductivity. Many people have shown that you can change superconductivity, you can enhance superconductivity, you can make superconductivity worse, but to take, well, as my colleague Kyle Shen would call it, a vegetable, and to strain it and turn it into something exciting like a superconductor, this shows the power of strain. Okay, so here I'm showing you control samples as well as a bulk single crystal of ruthenium oxide. They're nice metals to very low temperatures. But what we found is that if we put the ruthenium oxide on titanium oxide, so it's a rutile, here's the crystal structure. These are top views of the films that we've made on two different orientations of titanium oxide, rutile, substrate. So perovskites grow well on perovskites, rutiles grow well on rutiles. TiO2 is the only commercial rutile oxide substrate. Okay. So the way that we've done different strains is by using different faces of that rutile substrate. And on the 110 face, if it were fully commensurate, it would correspond to compressing the C-axis of ruthenium oxide by 4.7% and stretching it in the plane by about 2.3%. Here's another orientation of just to compare it to, and these both have fairly low surface energy, so they're good directions to grow in. The 101 direction is a much lower strain in comparison, so it's about 2% in one direction and close to 0 in the other direction. Okay, and you can see that the big change that it makes. A starting place is to look at X-ray diffraction and see, are these films commensurately strained, and do they behave like you expect them to? And indeed, if we look at the position of the out of plane peak compared to where it would be in bulk, indeed, for both strain states, things shift in the right direction. So here we're putting on mainly biaxial compression in the superconducting case of interest, which should elongate it in the out of plane direction, which it does. And in this case, we're putting it in biaxial tension, which should be the one that causes it to shorten in plane. And you can see that the film peak is shifted to the right of the unstrained peak. So it behaves like it should in that sense. Our electron microscopy collaborators have had a look at this. These strains are huge. Okay. Here's the ruthenium oxide film looked over a wide range, and if they zoom in, there are regions that look well ordered. There are also some regions that don't look as well ordered. Okay, but I'm showing you representative regions of the film, and notice it's very thin. When the film gets thicker, it definitely starts to relax. We've gone to the synchrotron to have a look at the relaxation. This is a reciprocal space map made on one of these thin superconducting films. This one's just 14 nanometers thick. If the various boxes here are telling you where you would expect the peak of the film and the substrate to be, if it's commensurate or not commensurate, the substrate, it should be where this white box is. So that's where the bulk reflection of TiO2 is. That's the substrate. The film, if it's fully commensurate, should be very, very close to it. If it's fully relaxed, the film peak should be way over here. Okay. Now, when we look at it, it's hard to see, that maybe it's relaxed a little bit, but it's certainly not way over there. And if we make it thicker, it becomes, so instead of being 14, this is now 21 nanometers. You can clearly see there's a lot of intensity from a partially relaxed. It's not fully relaxed. I mentioned, from Matthews and Blakesley, well, just bringing in dislocations is they don't suddenly come in. They start to relax the film or cracks. So there's certainly a component of the film that is partially relaxed. There may still be some that's commensurately strained. It's hard to see. But as you'd expect, as it just coming back to this one, you see that intensity is missing. But it has a definite effect on the properties. Now, coming back to the properties, I just thought I'd tie this to what our collaborators have calculated from first principles calculations. This is using DFT GGA with spin orbit coupling in it, and they can change the value of U and blah, blah, blah. Okay, but the important thing to say is that what's robust about the calculation is that the density of states that's near the Fermi level increases for this strain state of putting 5% compression along the C-axis. So from a theory perspective, it looks like it's taking what would be a degeneracy among the T2G levels, which you heard about again from Antoine Georges earlier, and lifts that degeneracy and pushes from where bulk should have its peak in its density of states, pushes them towards the Fermi level, which you would expect to have an improvement in TC just from looking at this standard superconductivity theory. My colleague Kyle Shen is able to look at by ARPAs and see what is actually happening to the bands. And what he sees is that if we go from this more relaxed film to one that is more highly strained, indeed, you can see that here's the angle integrated, you can see that there is indeed a shift in the density of states toward the Fermi level, which is consistent with what theory is pointing out here. Okay. Now I thought I'd also show another non-perovskite system with a crazy value of strain. Okay, a rock salt, and here the strains that we're trying to impose on europium oxide by growing it on LSAT are over 6% biaxial compression, and you must think, this guy is totally off his rocker. But let me point out that my postdoc has gone to incredibly low growth temperature. This is again an advantage of getting away from the perovskites. Rock salts can be grown at very low temperatures. Like the famous example, magnesium oxide was grown by Peter Flynn at negative 100 degrees C. So just to give you an epitaxial magnesium oxide rock salt. So it's possible to grow rock salts at nice low temperatures. And if you're trying to impart huge strains and not give the system another way of accommodating that strain, for example, by the formation of dislocations or cracks, okay, low temperature is a good route. Now, for this example, this is theory from Philippe. Philippe is one of the speakers at the, so again, this is an unpublished example, but from theory, the europium oxide was predicted by well, you can see all the theorists here, Philippe, as well as Nicolas Spalding, and Eric Bouzet, all predicted that europium oxide, which normally is a well-known ferromagnet, okay, it's got this europium 2+, half-filled F shell, but it doesn't have the ferroelectricity. But what they predicted is if you strain this thing enough, and in their calculations here, you can see the strains are huge. So they're saying that you need, it's of order 6% strain, giant strains to get there, that you should be able to make the europium oxide simultaneously ferroelectric and ferromagnetic, similar to the Europium Titanate example that I talked about early on. To try to do such heroic strains is not easy, and my postdoc worked on this for years. The method that worked for him was to make a superlattice with just 2 unit cells of europium oxide and then 2 unit cells of barium oxide. So it's like a strain layer superlattice. The strain is going back and forth and back and forth. The whole thing is grown on LSAT, which imposes, so the entire structure is commensurately strained to the underlying LSAT substrate. So that imposes a strain on both the europium oxide and the barium oxide. And on the europium oxide, it's over 6%. And Stanislav Kamba, who has looked at the soft mode in these superlattices compared to the soft mode prediction. So here you can see that a softening is predicted to occur, and where that mode becomes unstable, that it indicates going from a stable well to a double well, like a ferroelectric would have. And he can see optically that instability come about at about 100 Kelvin in this hugely strained film. So this is consistent with ferroelectricity, and we also can measure directly on the films the ferromagnetism. So it's a very simple multiferroic made possible by this strain engineering. So I wanted to give you a glimpse of, I know I've taken a long time to talk about just one of these knobs, and I think that's a good one to stop with for today. And the others are nowhere near as detailed, but for strain engineering, show you what it's capable of as well as what its limitations are. Jean-Marc, with that, I'm hoping that there are some questions.
Thank you very much, Darrell, first.
Thank you.
Thank you very much for this beautiful lecture, also for this very clear talk, and also for sharing with us these exciting results. You know, this ruthenium oxide, which is becoming superconducting, this is really wonderful. So congratulations. We are in fact running out of time, but I think we should just have a couple of questions. I think for everyone, I mean, you should maybe write down your questions, and maybe on Wednesday you will be able to ask all the questions you want to Darrell. Maybe I relay a couple of questions. The first one is okay. Now we are back in your lecture to the formation of misfit dislocations in strain films when you go above the critical thickness. And the question is which is coming from Sitao Wang, is what is the driving force to push the dislocations down to the interface between the substrate and the film?
Okay. The answer is it costs energy to strain the film. So by pushing them down, I strain less and less of the film. Can you see my slide or not?
No.
Okay, I'm not a Zoom master. Somehow.
not yet.
I tried. Let me try again. Okay. How about now?
Yeah.
Okay, good. Okay, so the idea is it costs energy to strain the film. So if you are just putting your dislocations at the surface of the film, yes, you can relieve the strain above that point, but only by pushing the dislocations down to the interface do you relieve the strain of the entire film, which is what's adding up to give you this big strain energy. Now, dislocations can be hard to move. Okay, and we're dealing with nice brittle materials that that glide may not be possible in this material. Okay, so maybe it's going to crack. But anyway, they would like to make their way down to the interface.
Okay, very good. Thank you very much. I will just ask you two more questions, which come from Ruby and Divine, related to europium titanate now. And you explained that europium titanate, when grown on strontium titanate using PLD, is ferromagnetic, but not when you use MBE. And the question is okay. So what is the difference between these films grown using these two techniques? And Divine was asking if it could be related to eventually a change in the concentration of oxygen vacancies. So the question is, I think, why do you get non-magnetic films using MBE and ferromagnetic films using MBE?
Okay. It's a great question, and I should point. I think it has two things. I think there are two aspects of this. So let me start with. Okay, I may answer it better next time when I get the right slides. But europium titanate we want to have europium 2+. Europium would like to either be metal or it would like to be europium 3+. Okay, it takes very low oxygen pressures to get europium 2+. So that's part of the challenge. And so that's a challenge already if you're trying to make an oxide and you're trying to make something that just wants a little bit of oxygen. When you're growing this by PLD, the natural thing to do is to grow at low pressure. Now PLD involves energetic species. When the laser interacts with the substrate, the ablated species come off with tens or even 100 electron volts of energy. If you're doing PLD under common conditions, which are higher pressures, maybe 100 millitorr, those species undergo a lot of collisions on the way from the substrate to the film. And when they get to the film, they can have much lower energies and not give rise to bombardment effects. I think that what's going on in these results is because they were growing at low pressure, they had bombardment effects. And I say that because some of these same groups also grew strontium titanate on strontium titanate by PLD. And as they change the pressure, as they go to lower and lower pressure, they also see a peak of the strontium titanate film that is not overlapped with the peak of the strontium titanate substrate. So, strain aside, octahedral rotations aside, if strontium titanate on strontium titanate, the peaks don't line up, something is wrong. Okay, so that's an example of where bombardment can cause issues.
Okay, thank you very much, Darrell. I think we will stop here. There are more questions related to your superconducting ruthenium oxide, but since I also have questions, I think we should really keep them for our question and answer session that we will have on Wednesday. So again, for everyone, if you have questions, please write them on the chat on Wednesday, and after the talk, I will give you the word for asking questions. So I think we will stop here, Darrell. Once more, thank you very much for this beautiful lecture. That was really great. Thank you.
Thank you.
And see you all on Wednesday. Bye-bye.
Okay. I look forward to more questions on Wednesday. Bye-bye, everybody. Have a great day.